Before going too deep into inverse functions, there is an important property that all inverse functions have, and we need to make sure that we understand it clearly. It's this property of being injective or one-to-one. They are synonyms, so use them interchangeably. But the idea of an injective function, and you can read the definition, it's a little technical, but the idea is that if we have equal y values, so I'm just going to write this in maybe an alternative way. So equal y values means that we have equal x values. Okay, so in other words, if we're at a certain y value and we have that, if we have equal, if we're at a certain y value, that means that the x values that we have must be the same as well. So, and it's called one-to-one because really it does give you this idea that at every x there's exactly one y and there's no other y's there. But more importantly, you actually have to think about it in reverse. So if we're looking now, instead of x is at y, so if we're looking at a particular y value, there's only one x with that property. Okay, so what we can think about is I'm going to draw two examples. Okay, so here would be, I'm just going to draw a nice smooth curve like this. Okay, I'm going to call this f of x. And then I'm going to do another one. I'm going to do it in black this time. Actually, I'll do it in blue. Let's do something like this. Okay, we've seen these functions perhaps in our past. Call this g of x. But again, the idea is that if we're looking at a particular y value, okay, so again, we're looking at y value. So at a particular y value, there's exactly one x value, right? If I'm looking here, again, I'm looking horizontally, and there's only one x value where with that particular y value. And down here, for instance, okay, there's my y value. Okay, go over, and I see that there's only one place where the function or only one x value that has that y value. Okay, now if I go over to this side, again, pick a y value, and then I'm looking along that y value, okay, I'm actually finding that there's one x value here and one x value here. Okay, so this function so f of x here, I would say that this is one-to-one. This one over here, there at a particular y value, there's two x's, so this is not going to have that one-to-one, not one-to-one. Okay, and so what I did in this in these examples here is do what we call as the horizontal line test. We have to have the vertical line test, right? Vertical line test determines if it's a function or not, but the horizontal line test determines if it has this one-to-one property or this injective property, and thus, well, it'll have an inverse. Okay, we need it to have this one-to-one property in order for it to have an inverse. Okay, so let's just go through and see if the following examples are injective or not. Okay, so we have F, G, H, and J. Okay. All right, so I can imagine plotting these. I'm just going to do maybe a rough sketch. 4, -5 is down here. 6, 1 is over here. 2, 4 would be up here, and 0, 3, something like that. Okay, is this injective? Yep, I can do a horizontal line, and that's going to only intersect my function once. Okay, G. Okay, I'm going to look at G. So I have 1, 0, 3, 0, and 4, 1. Is that going to be injective? No. Right, yes. Okay, because again, I can take a horizontal line through y is equal to 0, and it's going to intersect twice. Okay, 4 over x, I might need to do a little bit more work to understand what that looks like, maybe put it in a graphing utility. More or less what it looks like is something like this. We have a piece here, and we'd have a piece here. Something like that. Okay, is this one-to-one? Well, might need to check, but lines, 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 I'm only intersecting the function once, And again, you can verify with a graphing utility with a more precise sketch, but this one is actually going to be one-to-one. Yes. Okay. And the last example with this particular format is x squared plus 1. So we shifted up 1, and then we'll see this function family later in the course. But we have something like that. And then this was like that previous one that we did. This one, nope, we have two y value, or at a certain y value, we have two distinct x's. That cannot happen. Okay. Now we have a couple other ones that are given in graphical form rather than algebraic form. Okay. I guess another thing that you could do is ask yourself, if you fix a value of y, so let's say, I don't know, let's say y is 4, okay? Substitute that in, x squared plus 1, and then solve it, 3, x squared. Okay, if you solve this, you get x is equal to plus and minus square root 3. As soon as you have the plus and minus algebraically, that means you have two x's for one y, right? If they're invertible, that can't happen, okay? So be on the lookout for that if you're doing the algebraic work. If you have two x's for one y, then it violates that one-to-one property. Okay. Graphical forms, again, these are a little bit easier. Horizontal lines, yep. And so this one does have that one-to-one property, okay? This one, interestingly, it has it is one-to-one. So it is yes, but don't forget that that the function has to be a function, right? It has to pass the vertical line test, but it's not a function. Okay. So all this said, what do we take away? We have the one-to-one property, or we have the property of injectivity, right? We're looking. It'll have this property if at a single y value we have one and only one x value for that y value. And if we have more than one x value at a certain y value, then it does not have this property. You can use the horizontal line test to check for this injective property. And the upshot of all this is, when we're working with inverse functions, or functions that are invertible, they need to be injective. We need them to have this, otherwise we're going to get stuck. So we'll work a little bit more with this property in the upcoming videos.